Hello everyone, how are you all doing? Hope you're doing well. My name is Panda, and in this video we will talk about the third design pattern in chapter 2 of the book Machine Learning Design Patterns. As we have seen in the previous patterns, we will go through the problem we face first. Then we will see how the pattern we're discussing today can solve the problem. After that, we will discuss the advantages and disadvantages of using this pattern. So let's start with the first point, which is the problem. Let's jump straight into an example so we can better visualize why this is a problem. Imagine that we have two features, x1 and x2. Our goal in this problem is to predict the sign or the class of the given points, which are represented by these two features. Is the class positive or is it negative? Just by looking at the image, we can immediately notice that the data here is not linearly separable. Meaning, in this case, if we try to draw a single line to separate the two classes, we won't be able to. This is due to the way the data is distributed around the graph. Anyone who has encountered this problem in a college course has mostly likely seen it in a deep learning course. And usually they tell you, since the problem is nonlinear, we will need to use a neural network to learn the nonlinear relationship in the data. If we compare it to a logic gate, we can say it's similar to the XNOR gate. So, where is exactly the problem here? The problem is the data is nonlinear, which means we need to use a more complex approach to solve this given task. But is this the only solution we should immediately turn to whenever we face a similar problem? In reality, no. And actually, the example we just discussed will introduce today's pattern, which we don't even know its name yet. We will see what it does in this case and how it allows us to solve this problem using a simple linear model. With that, let's introduce today's pattern, which is called feature cross. The first question that comes in mind is, what does feature cross means? And to understand it, I need to go back to a very important point that I didn't mention when explaining the previous example. Whenever we get a problem, we try to format the data in a way that is suitable to feed into a model. Whenever we get a problem, we try to format the data in a way that is suitable to feed into the model. But just because the data is formatted correctly doesn't necessarily mean the model will learn from it. In other words, not everything we provide to the model will be useful during training. Some features are more important than others, and some features can confuse the model more than they help it learn. Not only that, but sometimes the features we have on their own might not be useful. However, if we combine, subtract, multiply, or apply any other operation between them and store the results as a new feature, this new feature might carry information that helps the model learn better. This process of taking existing features and engineering new features based on them, leveraging your domain knowledge to improve the model's learning, is called feature engineering. A simple example would be Uber. Let's say we have a dataset with two features, the start time of the ride, the end time of the ride. And the goal is to predict the ride fare. These two features alone provide some information about the fare, but it's very basic. For example, does starting a ride at 10 p.m. differ significantly from starting it at 3 p.m.? Yes, there might be a difference, but it doesn't directly tell us much about the fare. However, if we create a new feature representing the difference between the end time and the start time, now we have a much stronger feature that can help us predict the ride fare. This doesn't mean that knowing whether the ride started at 10 p.m. versus 3 p.m. is useless. It might be still important, for example, to determine whether the ride was during rush hours. 3 p.m. is usually busier than 10 p.m. But this new feature gave us a stronger signal to predict the fare itself. This entire discussion highlights the importance of feature engineering. Now back to our main topic, feature cross. Feature cross is a type of feature engineering as we explained. It works by taking two categorical features and multiplying them to generate new features. For example, if we take our previous classification example, instead of having x1 and x2, let's assume we have four categories. Category A, which equates to x1 greater than 0. Category B, which equates to x1 less than 0. Category C equates to x2 greater than 0. Category D equates to x2 less than 0. So we converted x1 from a continuous number into two categories, A and B. And we did the same for x2, turning it to C and D. Now if we multiply these categories to generate new features, we get AC, AD, BC, and BD, with each being a separate feature. As you can see, now the graph is divided into four squares. with each one having its own sign, instead of a scattered set of points. If we consider each square as a separate feature, the model now has 4 different weights to learn from. This way, this feature only corresponds to one sign, making the problem solvable using a linear model, instead of using more complex models that needs to learn the relationships between the features during training. We have explicitly provided these relationships by creating separate feature categories. Rewatch this part if it feels confusing because it's important. Feature cross allows the model to learn feature relationships faster. Yes, models like decision trees and neural networks could learn these relationships on their own, but the reason feature cross helps is that it simplifies the problem and allows a linear model to solve it. This means the model learns faster, reducing training time and costs. It also reduces the complexity of the model, which means we need less data compared to training with a complex model. Actually, let's apply feature cross to our Uber example to make it more practical. Imagine we have the following features in our dataset: the pickup time, the latitude and longitude of where the ride started and ended, and the fare, which we are trying to predict. If we want to train a model to predict the fare, the data we have is useful, but with feature cross we can extract even more valuable insights. So, what features can we use, and how can we improve them? Pause the video and think about it for a moment. There are many possible transformations, but let's start with the easiest one, the pickup time. We can break it down into 2 new features, the hour of the pickup, the day of the week. This makes sense logically, but here's where feature cross comes in. Instead of treating these as 2 separate features, we can cross them together to create a new set of features. Why? Let's continue the previous discussion about price differences at different times of the day. Is there a difference between 10 p.m. on a Tuesday and 10 p.m. on a Friday? Of course. Tuesday night is just another weekday night. Friday night is the start of the weekend, when more people go out. If we don't use feature cross, the model will have to learn this relationship on its own. From lots of data. Instead, we explicitly create a feature that captures the combination of time and day. So instead the model is struggling to learn this pattern, we give it a direct feature that tells it whether it's a busy time or not. As you can see in the picture, Saturday at 3 p.m. is different feature than Sunday at 2 a.m. This allows the model to instantly recognize which time slots are high traffic and adjust fare predictions accordingly. As a result, by applying feature cross, we went from 2 features to 168 features, 24 hours times 7 days. But this actually helped the model learn better and faster. When we trained a simple linear model with these new features and compared it to a deep neural network that had to learn these patterns on its own, we found that the linear model performed just as well as the neural network, maybe a little bit better. But here's the crazy part. The linear model only took 1% of the training time needed for the neural network, which showcases the true power of today's design pattern. Another example where feature cross is useful is in the polarity, which we discussed in the last video. By crossing gender and polarity, we make it easier for the model to distinguish between twin boys, twin girls, triplet boys, and a single boy. Instead of treating twins as one general category, the model instantly understands the difference between boys and girls as twins, without needing extra data and without having to try to learn this connection from scratch. The book also mentions that feature cross isn't just for simpler models. You can use it in deep learning too. In the Uber example, when we created 168 new features, we can feed them into the neural network in 2 ways. First one is the one-hot encoding, where only one feature is 1 and the rest are 0. The second way is through the embeddings, which transforms these features into dense vectors before passing them to the network. We will talk more about the embeddings later. Now that we have discussed the problem and how feature cross helps solve it, let's look at things to watch out for when using this pattern. The first thing is numerical features. Feature cross doesn't work directly with continuous numerical values. So the first step is to convert them into categories, also called bucketing. For example, in our Uber dataset, we have the latitude and longitude. Instead of keeping them as raw numbers, we can group them into regions, like Manhattan, Queens, and Brooklyn, etc. This allows us to cross them with other categorical features easily. Then we go to the second issue, which is the high cardinality. We talked before about how too many sparse features can make learning difficult. In the Uber example, crossing day and hour created 168 new features. What if we cross even more features? We would end up with huge sparse vectors, which makes it harder for the model to learn. Instead of dealing with large sparse vectors, we can use embeddings design pattern, like we discussed in the previous video. Embeddings convert high-dimensional sparse features into lower-dimensional dense vectors, which store meaningful relationships between features. This helps the model learn efficiently without the issue of sparse data. Finally, for the last point to keep in mind, when we cross high cardinality features, we generate a huge number of new combinations. But the problem is, some of these combinations will have very little data. For example, before feature cross, if we looked at rides at 12 p.m., we might have 100 data points. After crossing hours with days, we might only have 12 rides for 12 p.m. on Thursday, and 9 rides for 12 p.m. on Tuesday, and so on. This makes it harder for the model to learn properly, because it doesn't have enough examples for some combinations. As a result, instead of generalizing, the model might just memorize the few cases it sees. That's why feature cross works best when you have enough data. When you have enough amount of data to ensure each new feature has enough examples to learn from. A solution to this problem is regularization. To handle high cardinality feature crosses, the book recommends using L1 or L2 regularization. L1 regularization acts as a feature selector, eliminating unnecessary features by setting their weights to 0 during training. L2 regularization helps prevent overfitting by reducing the size of the weights, making the model simpler. When we added regularization to the linear model in our Uber example, the RMSE improved by 0.3%. And that's basically it for today's video about the feature cross design pattern. In summary, we didn't just discuss the problem, we also explored how feature cross helps solve it, and what to watch out for when using it. And that's the end of today's video. Hope you found it useful. If you have any questions or feedback, drop them in the comments. See you in the next video inshallah with a new design pattern. Bye bye.